Hi everyone, my name is Savannah and welcome to my Local Expert 3 project. Today I'll be talking about SPR. First, what is SPR? SPR stands for surface plasmon resonance. It's an optical technique used to measure molecular interactions. One of the interactions are protein-protein interactions, which we've discussed in class. It is used to measure the kinetic and equilibrium binding constants as well. How does it actually work though? It works by using plain polarized light that hits a metal film under the total internal reflection conditions. The signal is dependent on the refractive index of the medium on the sensor chip. When molecules bind, the refractive index changes on the sensor surface. One protein is immobile on the chip, and the other protein is measured under flow. The response is then measured in resonance units and is proportional to the mass or the number of molecules bound on the surface. The response is then recorded and displayed as a sensogram in real time. First, how does SPR compare to co-immunoprecipitation, a method we discussed in class? Using SPR is a lot less time-consuming than co-immunoprecipitation. That is because you can skip the step of adding tags since SPR is label-free, whereas in co-immunoprecipitation it's required you use some type of tag, like a fluorescent tag. Compared to ELISA, another method we discussed, SPR seems to be the better option overall. ELISA can measure and quantify high-affinity proteins but can only give insight into the biomolecules of interest present in the sample, but doesn't offer info on kinetics between the target and bound molecule like SPR can. ELISA also requires tags, whereas SPR does not. SPR is quicker than ELISA because it also has fewer steps, and SPR overall is more in-depth since SPR allows you to observe things in real time, whereas co-immunoprecipitation and ELISA do not allow you to do so. Some controls for this technique are having a buffer for pH, having flow rates, the isoelectric point, regeneration conditions, purity levels, mass transfers, ligand concentrations, and analyte concentrations. So first, you need to set up optimal concentrations of the analyte and ligand and choose 5 concentrations that reside between 0.1 to 10x of the expected KD interactions. Another control is the pH needs to be adjusted to the isoelectric point of the analyte. A baseline also needs to be established by running the experiment with the buffer alone to see if the system has interactions and to give the system a reference point. Negative controls need to be run with components that aren't expected to interact. This would be like using a protein that's not expected to interact with the target protein. The positive control should also be run using a component that you know will interact, so you can validate the sensitivity and specificity of the assay. And then the regeneration control is needed so you can regenerate multiple cycles for the analysis, so you would need to wash the surface and remove previously bound molecules before running the regeneration. What are some advantages of this technique? The biggest advantage is real-time monitoring. Other methods like the Western blot and co-immunoprecipitation can only let you know if binding is happening, whereas this method can show you in real time. SPR also allows you to see on and off rates and affinity values in real time. As we've already established, SPR is label-free, so you can skip the step of adding fluorescent tags. And then this method also utilizes small sample sizes, so that makes it more affordable and less time-consuming. You can also reuse the materials like the sensor chip, which lowers consumable costs. And lastly, you don't need to purify samples, which also cuts down cost and time. Like any method, though, there's still limitations. One limitation of SPR is that it's unable to discriminate between specific and non-specific interactions with the sensor surface. One way this can be avoided is using reference material to correct the non-specific binding. Another limitation is that it's not mass sensitive. This means it can have a hard time detecting low molecular weight compounds. And finally, there's also a limited sensor area, which leads to diminished capacity. So you would need to either increase the sensor surface or do several runs to lessen the limitation. So now I'm going to go over 3 different papers that utilized SPR in their research methods. This first figure is from a paper that was looking at the structural comprehension of bacterial type 6 secretion systems to characterize the TSSJ to TSSM complex in E. coli pathovar. Both figures are illustrating the interactions between the TSSJ and TSSM ecto using surface plasmon resonance. In figure 3a, when TSSM ecto was injected over a chip coated with TSSJ, it showed a quick release without needing chip regeneration, indicating that there was an interaction between the proteins. And then in figure 3b, it's showing the dissociation constants, which is KD, for the interaction. So it's showing that by injecting TSSM ecto over the TSSJ coated chip, it resulted in a KD of around 2.1 plus or minus 0.25 microns, indicating that that was a relatively stronger binding. And then injecting TSSJ over a chip coated with TSSM ecto showed a constance of approximately 4.0 plus or minus 0.5 microns, suggesting that that is a slightly weaker interaction compared to the previous interaction. So the KD values are quantifying the strength of the binding between the TSSJ and the TSSM, supporting that there's an understanding of the interaction dynamics. This second image is coming from a paper that was looking at a novel protein-protein interaction of Yersinia pestis type 3 secretion system, and it's showing that SPR was used to examine the kinetics and binding affinities of the various protein-protein interactions. So the researchers utilized SPR by immobilizing one of the interacting proteins onto a sensor chip surface and then flowing the other protein over that surface. This allowed for the monitoring of the binding and dissociation of the proteins in real time. And then the resulting sensorgrams in the image show the association and dissociation phases of the interactions as they change in the refractive index. Overall, this image is showing that the sensorgram was able to see that there were select protein pairs exhibiting strong interaction. Finally, this last figure is from an experiment that was trying to decipher the XCP Pseudomonas aeruginosa type 2 secretion machinery. So it shows that the SPR sensorgrams showed specific interactions between the substrate and the various components, and then the sensorgrams depicted binding events between the LAS-B and the UHVIWJXK complex, as well as individual interactions with the UHVIN-XK components. And then the sensorgram is displaying a change in the response units over time, showing that there's binding and dissociation kinetics of the LAS-B with the components. So it shows that there's a direct interaction between the LAS-B and the quaternary complex of the components located at the tip of the pseudopilus. So specifically, it's showing that 3 out of the 4 domains, which would be UH, VI, and XK, show that there's binding to LAS-B, while the WJ doesn't exhibit notable binding in the experiments. Overall, the figure is showing that there are binding events that are specific interactions between the LAS-B and the specific components that are UH, VI, and XK. And here are my citations. Thank you for watching, and good luck with the rest of your semester.